Okay, so we are in the packet today. Yes, okay. You should have watched a video before class today. If you didn't, you're going to be a little bit lost today, and then you'll have to watch that video and then rewatch this video, and then you'll be back to where you should be because you forgot to do something this weekend. Okay? Tomorrow in class, we are going to have a formative at the start of class. Then we'll give you a worksheet to work on after the formative is done. Thursday, because the afternoon classes don't meet, so Thursday is just going to straight up be a work day for you. Okay? Friday, there will be a video on Canvas, because remember, Friday is our independent learning day. So Friday there will be a video on Canvas and a note sheet to fill out along with, and that is what you have to do for this class. Okay? Okay. Chromebooks and earbuds. Mrs. Hill is gone tomorrow, so that's why her classes are going to be watching the video from class that I put in. So that's why the Chromebooks and earbuds are on there for Wednesday. Thursday is just kind of more of for because it's a work day type of deal. So okay. All right. So we are going to be solving logarithmic equations today. Okay? Now, what you should have learned by watching the video over the weekend is when we are solving with logs, you need to know, or let me rephrase that, you should have memorized by now base to a power equals an argument, we call it, is the same as log with the base of the argument equals the power. Should move that over. Hold on, tap the brakes. Let's make this look pretty. Okay? So if you don't have that memorized yet, you need to get that memorized. Logs, exponentials, all that stuff becomes dramatically easier if you have that memorized. Because in order to solve exponentials, you switch it to logarithmic form. In order to solve a logarithmic equation, you switch it to exponential form. Okay? That's the first thing that you do. And then from there, you solve. Okay? So this, number one, is in logarithmic form. I need to solve for x, so I need to take it from logarithmic form, and I need to put it in exponential form. Well, when it's not written, it is assumed that the base is 10. If it is not written, it's assumed that the base is 10. So 10 is my base. -2 is my power. X is my argument. It's what I'm looking for. 10 to the -2 power is 1 over 100. And that is how we solve those. Okay. In number 2, 2 is my base. 4 is my exponent. X is my argument. 2 to the 4th power, 16? 2 times 2 is 4, times 2 is 8, times 2 is 16. In natural log cases, same thing. Okay? Natural log is just log base e. So then this would be e cubed is x, which for us is much nicer, is much cleaner, is much easier than e to the third. 20.0855. Right? Number 4 should be the square root of 10. Because it's 10 to the 1/2 power is x. So we can just leave it as square root of 10. Again, I would also accept there. I'm not going to say I wouldn't. I'd accept 10 to the 1/2 power. It's clean. It's nice. Any questions on that? Awesome sauce. Okay. So graphs of logarithmic functions. Remember, so b to the x power, y equals b to the x power, is a exponential function. Okay, so an exponential function I'll put here in purple. Okay, so it would grow like that, right? You would have y equals 0, and it would grow like that. It would go through the point 0, 1, right? Right? All that stuff. We did that last week. Yeah? Okay? Logarithmic functions are inverses of that. Now, in an inverse, we take the x and we make it the y. And we take the y and we make it the x in the inverse. So, if that's the case, then in my new function, in my logarithmic function, then I would go through the point 1, 0. Because my x becomes my y becomes my x. I switch my x and my y. Instead of having a horizontal asymptote at y equals 0, what is my logarithmic function going to have? Vertical asymptote at x equals 0. Yep, so that part's going to stay the same. Or I shouldn't say stay the same. That part will change. So if we think about it, we had negative x and a small positive y. So that means I'm going to have a small positive x and a negative y. It's going to come through and look like that. Okay. So the domain of my first one was all real numbers. My domain of my inverse then, so the domain then becomes my range on the inverse. So those two have that one. My range on my purple one was y is greater than 0. That range now becomes my domain over here. So if we have a special base, 10 common log is the name of it, a common log. If we have that, we're still going to have okay? So we're still going to have x equals 0 as our vertical asymptote. We're still going to start close to our asymptote. And then we're going to expand out, and out. If I wanted to find some points that we go through and label those, we would go through the point 1, 0. Because if I put in 1 for x, log base 10 of 1, what exponent do I have to put onto 10 to get 1? 0. Okay, so that we go through that point. Give me another point that this graph, this function, would go through. Another point on the graph. Once you see the pattern, what exponent on 10 do I have to get 10? 1, right? So what's that point? Give me another chance. 10, 1. Give me another one. Oh, put that calculator away. 100, no. 100, 2. Give me another one. 1,000, 3. Give me another one. 10,000, 4. Another one. 100,000, 5. Million, 6, etc. See how it's growing? Like it's really expanding like an exponential, but it's really expanding now to the right. It's not growing very much vertically because at a million, at an x value of 1,000,000, we're only up to 6. Okay? Much like an exponential. An exponential grows rapidly vertically, but it doesn't really grow very much horizontally. Okay? Those inverse relationships. Okay? So there's 3 points on it, and we came up with 6 more. Okay? Natural log of x, again, same function. Okay? Or a different function, I should say. Same thing, let's graph it. Still going to have x equals 0 as a vertical asymptote. Will it go through the point 1, 0? Because if I put it, because what's the exponent that I have to put on e to get 1? 0. Yep. So it still goes through the point 1, 0. Okay. What's another point that's on this graph? Nope, because it's not 10. This is e. Yep, this is log base e. Right? What exponent do I have to put on e to get e squared? 2. What exponent do I have to put on e to get e to the first? 1. So on and so forth. Okay? Logs are exponent functions. Logs are exponent functions. Okay? Now we have 3 properties of log. Okay? We have the product property, quotient property, and the power property. All three are great. Okay? But with logs, just so you know, the base of your log can't be 1. It's got to be positive. Everything else has got to be positive. All that fun stuff. Okay? All right? So here they are. If I am taking two things and I am multiplying them together in the argument of the log, okay, then I can take that and I can split those up. Okay? I can take that and split those up. What do you mean? The only worksheet that we've given out so far is that salmon colored one right there. Yep. Yep. Mm-hmm. Okay. So you can, if you're multiplying in the argument, you can split that up into 2 or 3 or 4 or however many things you're multiplying in, and they're separated by addition. If we're dividing, then we can separate them with a subtraction. Now those two, I mean, I want to say that we're going to use them a lot, but we're not really going to use those as much as the next. The third one we use a ton, and that's the power rule. If you've got a power, an exponent inside your argument, you can put that out in front. Product and quotient rule, do they help? Yeah. When we're writing out logs, I mean, it makes stuff look nicer because if you have log base 3 of 9, you don't have to write out log base 3 of 9. You can write out 2. Okay? So if you have something like log base 3 of 9x, well, that's just going to be 2 plus log base 3 of x. And we'll get to that here in a minute. Okay? But that's where we use the product and the quotient rules. Okay? This next one, if you are using one of these, you don't need. Okay? I think one of the Casio scientific calculators does this too. But what this is doing is called change of base. So if you're using one of the regular old TI 30s, one of those blue ones that like everybody and their brother has, okay, right? If you're using one of those, that you have to use a change of base formula. So that's why we teach it. Okay, but now as technology is increasing, like up here, you just type it in as it looks. Okay? The change of base formula is that you can either have log of u divided by log of b, or you can have the natural log of u divided by the natural log of b. Okay? So if we're asking you to find the equivalent, or what does it say in the change of base example? There it is. Does it say? Doesn't tell me what. It's one of those. Usually it's like approximate. That wasn't an E, it was an A rows. Approximate the log. Then we would have you use change of base. Okay? Okay? So, expanding logs, this is why we do it. So we've got 3 things in here that are being multiplied together. We've got that, and then we've got that. Okay? So the first thing that I can do is I can expand this log, and I can say, well, that is going to be log of 100 plus log of x plus log of y to the 5th. Because those 3 things were being multiplied together in my argument, I can expand those out into it. Now I can say to myself, self, log of 100. What exponent can I put on 10 to get me 100? 2. So this one here just becomes 2. Log of x is just log of x. I can't do anything with it. Log of y to the 5th power, I can use the power property, and I can say that that is 5 logs of y. Yes, you did. Okay. What exponent, because log without a base, it's base 10. Okay? So logs are exponent finders. What exponent do I have to put on 10 to get 100? 2.
Oh, okay.
Yep. If this was 105, I couldn't do that then, because I don't have a nice, pretty exponent to put on 10 to get 105. Okay? You try expanding this one. Natural log of x squared minus the natural log of y cubed, right? But then that can be 2 natural logs of x minus 3 natural logs of y. Agree? Okay. Expanding, we did that already. We're good there. We're good with 3 and 4. Yeah. Okay. Condensing. Now we're going to go the other way. Okay. So now we're going to do everything in reverse. So the first thing when we were expanding, the first thing you apply is the product or the quotient property. Then the next thing you apply is the power property. When we're going reverse, when we're condensing, getting it down to one single solitary log at the end, okay, you do those steps in reverse. So the first thing that you would apply would be the power property. So this would be log of x to the 1/2 power minus log of y cubed. Now, because it's subtraction, that means it's dividing. So this would be log of the square root of x over y cubed. You could do x to the half then, yes. But it also is square root. Here in number 6, normally I would have said, yeah, just go do it. Then go home. Yeah, let's do it. Okay? Or take it then. But here, because we got minus and minus, if you write it like this, then you would get, in the end, you should get the natural log of 2 divided by x y cubed. Okay? A lot of people will give me this as an example. Now, here's what I'm gonna. This is why I'm gonna do this one a couple of different ways. Okay? So we start back from the start. A lot of people go, oh well, that's the natural log of 2 minus the natural log of x. Yeah, which is the natural log. Oops, I put h. Which is the natural log of 2 over x, right? But then you've still got this minus 3 natural logs of y. So then they give me this. What's wrong with that? Other than it looks really scary. Okay? Fractions and fractions. We don't like fractions and fractions. We only want one single solitary fraction at the end. Okay? So you got to do a keep, change, flip. And when you do a keep, change, flip, keep, change, flip. Now you're back to here. Okay. And it's much cleaner, much nicer. Okay. I want to say, oh yeah, this one right here, number 8. I want to do number 8, and here's why I want to do number 8. Okay. Let's plan our work before we work our plan. Okay. So if we plan our work, give me the order. Multiplication or division. So we've got 1, 2, and 3, right? So what is the order of multiplication and division using the colors, the properties? We should, what should we do with 1 and 2? Multiply them or divide them? Divide them, right? Because it's a subtraction. What should we do with 3? Multiply it. So what you can do here is you can take these two and you can do them in any order. Because remember, there's no order in addition. So we could really write this as right? It's legal, right? X minus y plus z is the same as x plus z minus y. Good there. So this is going to be that. These two become that, which gives me my final answer of that. One single solitary log when you're condensing, taking it from one log to multiple logs when you're expanding. Okay? Last one is change of base formulas. Okay? So, as I was saying earlier, sometimes it's not necessarily the easiest to find an exponent that fits on 1. Okay? What exponent goes on 3 and gives me 8? I don't know. Right? Because 3 is not 3 to the first power is 3, 3 to the second power is 9, 3 to the third power is 27. None of those are 8. Okay? So what should this one be in between? Just based off of what we know, where should this answer, if I call this x, where should x fall on a number line? Between 1 and 2, right? Closer to 1 or closer to 2? Closer to 2, right? Okay, because 8 is closer to 9 than it is to 3. Okay? So it should be somewhere between that. So how we do this is on your regular TI calculator. Does anybody have one out? The blues or the pinks or anything like that? You could do the natural log of 8 divided by the natural log of 3. Now I will tell you that using those calculators, it opens opens up a set of parentheses when you hit log or when you hit natural log. You've got to close that parenthesis. So it'll give you like this. You have got to physically close that before you hit the divide. Okay? So it'll open up like this. You got to close it off. Same if you do common log. It'll open it up like that. Ooh, easy one there, Linsmer. Voice cracked a little bit there. You got to close that off before you hit divide, and then it would be log of 3. And then you have to close that off and then hit equals. Okay? On the TI, on the graphers, the ones that we have out there for us, the nice thing is that it does it for you. It's technologically advanced. So if you go into a calculator and you hit log, which is the control of the 10 to the x power, it sets it up for you. And so all you have to do is fill it in so that they look the same. 3 tab 8. Oops, got the brakes. Didn't hit. 3 tab 8. Okay? Now, most of the ones that we have set up are set up in exact mode. So it's going to say that is log base 3 of 8. Okay? To get it the decimal approximation, you hit control first, then hit enter. Okay? Control enter. And it, like we said, in between 1 and 2, closer to 2 than it is to 1. For when we approximate logs, we approximate to 3 decimal places. So I would call this 1.893. With me? Love it. Log base 4 of 16. Should be 2, right? Okay. Using change of base formula, we can figure out that if it is 2 or not. Verify on your calculator that you get 2 there. Okay. Then at the same time, I would like to know log base 4 of negative 16. What do you get there? What do you got? Non-real calculations or an error if you're using a TI, if you're using the TI-30, did you get an error? Why? Why would I get an error for this one? But why? I got a positive base, right? Taking it to a positive power, I got to get a positive number. Let's try one more, just because these are so easy to calculate. Let's go log base, give me a number. 5. I heard log base 5 first. Give me another big number. 220. Log base 5 of 220. Should be above 3, less than 4. Should be between 3 and 4. Should be closer to 3 than it is to 4. 3.351. If you don't close off that first parentheses, you get something totally different because your order of operation, it's going to take your numerator or whichever one you want and divide it by the log, then take the log of that. Okay? You have to close off that parentheses. 3.351. Boom shakalaka. Right?